I'm going to record this. There we go. Okay. So we start with number 3. Indefinite integral now the thing here is that there's no square here, so doing a trigonometric variable change is when you have a function as one of the limits of the integral. Yes, I will, but first let's start with that. There's a particularity here when you have a function. If you define a function in that sense, which I think is what you mean, or maybe you mean in determined integrals with infinite here. In any case, let's see if I can make this pen work. Good. It's new and it's already not working. Okay. So this is the story. I went to the storage room and picked up an empty pen for whatever reason. Anyway. Now I need a longer equality sign. There we go. Here our change wants to be something that makes this root easier. What can that be? We could say (3x + 4 = u), for instance. In this case, x would be u minus 4/3, and so the x is 1/3 of the u. So we put that integral sign here, and what we have is square root of u, 1/3 differential of u. This is x in power 1/2. So here what we have is this 1/3 that goes out. This is x in power 1/2. It's a polynomial on u. So the form of this integral is 1/2 of u in power 3/2. Now we unsubstitute. We return the substitution back where it belongs. And this is 1/6 3x + 4 in power 3/2. And since this integral is indefinite, we have to add a constant. Now, one question you all may have in your minds is, how do I know which change of variable, which substitution is proper for the problem? Okay, there are two references here. If you have a square root and the variable is squared, you have to go for trigonometrics. If you have a square root and a monomial in degree 1 here, you would go for linear change of variable. And otherwise, I'm going to have you do 100 integrals each week until you get this, because there is really no exact rule. Integration is an exercise of intuition most of the times. So moving on. We have number 5. Yes, we can. Let's pause this one for a while. If you mean this one, the substitution here is kind of intuitive, and we say square root of x equals minus u. Why minus u? You will see why. Here, x is u squared. Right? You can always do that. And so when we substitute, we get minus u here, 1 plus u, and something of this form. Now, I'm going to do a small trick here, and is add and subtract 1. And let's see what happens here. We can separate terms. Is this correct? Yes, it is. And we have the integral of this thing right here, and here, notice all this fraction is equal to minus 1. So this thing right here is u squared. And now moving on here, we can do parts. We could do like this. To u is v, and 1 over 1 plus u is differential of w. And so from here to the u is d of v. And w is like this. So what we have in that equation is vw minus integral of this thing right here, plus u du, and minus, let's see if this fits in the image, perfect, and minus u squared, that comes from here. Now, there's something there, right? Like integrating a logarithm should not be a trivial task. Well, it's not a trivial task by any means, but here we have to do another substitution. I'm gonna put it here. I'm gonna say this thing right here. So 1 plus u is in power t. And so differential of u is e in power t dt. So this thing, I'm going to save it. And this thing, I'm going to save it. And write this integral down. And we have minus 2 times the integral of t et differential of t. Now we can easily integrate this by parts. We call t is v and et dt is w. Sorry, is dw. So dt is d of v and et is w. So what we have here is minus 2 t if t plus 2 integral. Let's see if it fits the image perfectly. Of this product right here. Which is minus 2 t plus 1 in power t. So the full value of our integral, I'm going to delete this arrow to make everything a little bit more visible and draw it something here. Our integral, this thing right here is equal to u logarithm of 1 plus u minus u squared and minus this thing right here. Now what's left? What is left is for us to return all the variables to its rightful place. So with square root of x equal minus u, this is minus 2 square root of x times logarithm minus u squared plus x and minus 2 logarithm of 1 plus u plus 1 times e in power t, which is 1 plus u. 1 plus u is 1 minus square root of x. Now, does any of this cancel? Let's see, because this looks terrible. Honestly, this looks really bad. So we have minus 2 square root of x logarithm minus 2 logarithm minus square root of x. So this cancels out. And we have x minus 2, and the last term that they have to consider, minus with this minus plus, and it's 2 square root of x. Or something close. Did I do this correctly? It looks like it. So as you can see, integrals can get really messy. So you really have to get used to this type of manipulations. Also, there is a chance that this is wrong because I don't see where this how these two actually fits here, but you can assimilate it in the constant. So it may look something like that. Now, moving on. You may be wondering here, is there a possibility that I messed up some calculations? Yes, there absolutely is. But still, the idea that I wanted to transmit you here is that something that looks pretty simple, if you don't go for the proper substitution, can get really messy. It can get really, really, really messy. So let's go for this one and see what can be done here. Our idea here may be to think 4x squared plus 1 equals u, and we can definitely try that. And from here we have x squared is u minus 1 over 4. Something like this. And let's see what happens. So we do our substitution. First of all, u fourth there. Sorry, u fifth. This is power fifth. Second of all, x. X is this thing right here. Third of all, differential of x. This is good news. Why, you may be wondering, because now this thing with this thing have cancelled. We can take the 1/2 out of the integral, and what we have here is the integral of u in power minus 5 differential of u. For those of you who have been following the course, this is exactly minus 1/4 of u in power minus 4, right? This thing right here, n plus 1 is minus 4. So this is u minus 4 divided by 8, with a minus here. Now, we turn back. Since this -4 is here and what we have here is a power, we could theoretically move it here for the ease of manipulation. So this thing is -1 over 8 u fourth. There we go. Now, questions about this substitution? Okay, let's move on. Number 7. Ooh, this is a good one. If this was a minus, if this thing here had a minus, the integral would not be possible. But thank God we have a plus here, and so our change of variable, our substitution, here is elementary. What's the difficult element in this integral? In power x squared. In power x squared looks bad, so we're going to take the x squared out. X squared equals u. So x is square root of u, and the x is 1/2 u in power minus 1/2. Differential of u. So we start substituting everywhere. We have u in power 1/2 in power u, and 1/2 u in power minus 1/2 differential of u. Now we have the exact same amazing thing happen to us. This cancels with this. And since the integral of the exponential is the exponential, here it is. Now we only have to return the substitution, and we are good to go. Why do they cancel out? Because this thing negative exponent, positive exponent, so one is multiplying and the other is dividing, and they are the exact same thing, so they cancel. Precisely. When you derivate the square root, the result is 1 over the square root. If you want to see it more visually, this is what happens here. The square root becomes 1 over 2 square root, so it's dividing. Now, the next intuitive question may be, how do we choose the substitution? And I will probably make myself this question many times today. A good way to start is to think of what the most complicated part of the integral is and trying to smooth that out. So number 9. So ideas. We could take cosine equals u, maybe. We could take sine equals u. We could take sine square equals u. Since this one is not a square and this is a square, if we take the substitution over the square, here we will get a square root. So I'm going to try and see what happens if I do this change. Here, the sine square is 1 minus u squared. Again, trigonometric identities. So x is arc cosine of u. So the x is minus 1. This thing right here, it doesn't look too good. It happens. And now let's replace this. Up here we have u, and divided we have 4 plus 1 minus u squared. Minus. We have only made it worse, right? We have definitely only made it worse. So let's begin fresh. Obviously, this change didn't work. So the next thing that we can consider is the sine square, maybe. In this case, cosine of x is the square root of 1 minus u. And so dx, this cancels here, and this sine x is the square root of u. Okay, it looks bad, but it could be worse. So let's see what we have here. We have the square root of 1 minus u. We have 4 plus u here. And now when we multiply by the differential, we have 2 square root of u, square root of 1 minus u. Okay, here at least, these two things are going to cancel out. So we are already doing something. Now you may be thinking, maybe we should have taken u squared here, and you are absolutely right. Here I'm going to do yet another substitution, which is u equals t squared. Inverse differential of u is 2t differential of t. And so I get the integral of 2t differential of t 4 plus t squared times t. So this thing right here, look that these two and these two also cancel out. And this is the integral of differential of t divided by 4 plus t squared. Okay, now this looks pretty good. Like there should be something like the arctangent of 2t or something like that, right? Let me check one thing. Good. We are one step away. We know that if we have this, we have a tangent of -1, but here we don't have a 1, we have a 4. We have to make a 4 appear here. What I'm going to do is divide and multiply by 4 here. I've done nothing, this still works. And so I'm going to take these 4 out of the integral. The interesting part is that t squared over 4 is t halves squared. Now, this is 1/2 times 1/2, so I'm going to put one of the 1/2s inside. And now this is an integral that we know very well. And now t is the square root of u, so the sine of x. Okay. So if you don't have more questions about this exercise, I'm going to call this a break, take 10 minutes, and in those 10 minutes, since Philip's screen wasn't very clear, I will show you how the exercise, the first in assignment 5 is solved, just for the record, so you have a clear solution. Now, this thing right here. So we will start again at 1/4. In the meantime, drink some water, stay hydrated, stretch your legs. Doesn't sound important, but it is. So we have X. Which is this thing here. And we wonder about f prime in point pi. What's this? So we're going to derivate this by treating this as a product. The first term is x squared. The second term is this integral here. So we apply the product rule. And now we have an integral defined from any point to x of a function by using the fundamental theorem of calculus. This is no other than e in power cosine x. So moving on, we can now evaluate this in pi. In pi, this is 2 pi integral from pi to pi. This is 0. Because the interval that goes from pi to pi is absolutely nothing. This equation is equal to 0. And here we have pi squared e cosine pi. This is pi squared in power -1. Cosine of pi is -1. And so we arrive to Philip's solution, which was pi squared over e. There we go. The key here is a theorem that is called fundamental for a reason. Now it's break time for me as well. Okay, so it has been roughly 10 minutes. So let's go back to business. Now we find something that we may find scary at some point. One over x plus 1. What do we do here? A first approach could be to say simply ex plus 1 equals u, in which case we will see that ex is u minus 1, and so x is the logarithm of u minus 1 in absolute value, and so dx is the u over u minus 1. So let's plug this into the equation and see what happens. We have division here. Here we have u, and the dx is the u over u minus 1. Now, how do we solve such a thing? It definitely looks bad. So what I'm going to do is to split this into simple fractions. So we have 1 over u minus 1 is a over u plus b over u minus 1. And by the rule of sum of fractions, we have that a times u minus 1 plus bu equals 1. So a plus b is 0 because there is no u in the other side. And if we look at the ones, we have minus a equal 1. And from a equal minus 1, we get b equal 1. So this thing right here, we can write it like this. Now these two integrals are immediate. First one, logarithm of u. Second one, logarithm of u minus 1. So this is the logarithm of u minus 1 over u. This thing has a minus, so it divides. And this is no other logarithm of 1 minus 1 over u. If you want to say it like that. Which looks pretty bad. So I'm going to solve it here. And that will do it. This exercise is marked as challenging, as difficult, and the difficulty is here. When you find this fraction, you have to be able to see it as the sum of two simple fractions. Then you just solve it, no problem here, and in the last step, you return the substitution back where it belongs, and you get that thing right there. Another alternative that you may have used is in power x equals u, which is absolutely the same, but you get a plus here, this will be a minus, this will be a plus, and in the end you will arrive to the same result because indefinite integrals are uniquely defined. So no biggie here. This was challenging, but only in the name. And now let's move to section 5.7, if you guys don't have any questions about this. All right. Five 5.7.5 to begin with. We have two curves, and we want to find the area trapped between them. And second curve, is 2y plus 3x equals 6. Or if you want to see it in the other way, e equals 3 minus 3/2 of x. So I'm going to sketch this function, these functions. This thing has two zeros, in 0 and in 4. It's a parabola and it's sad because the coefficient in x squared is negative, so the parabola makes a sad face. It has a maximum in x equals 2, which is 4 as well. No, 4 times 2, 8 minus 4, yes. So it does something like this. Then it goes down. From this straight line, if x equals 0, e equals 3. And if y equals 0, x equals 2. So the area is this thing here. Now, how do we model this? In order to model this, we have to consider that this part is not taken. So first of all, I'm going to calculate this point x0, because our area will be given by the integral between 0 and x0 of this function. So the area trapped by this parabola in this space, and the area trapped between the x at that thing here, unless that's not what I'm being asked. No, that's not what I'm being asked. Ignore this. The area trapped between the two curves is this thing right here. Sorry, it's not this thing right here, because that's trapped by the axis. It's this thing right here. So, first of all, intersection points. When are these two functions the same? We put our system of equations. This comes here. So here x, this is a second degree polynomial equation, minus b plus minus the square root of this thing square minus 4 times this thing. So minus 12. Divided by 2a by minus 2. So this is minus 11 halves plus minus the square root of this thing divided by minus 2, 121 minus 48. Is this number here, which is prime. This is prime, so it's not a perfect square. This 4 comes out dividing as a 2 and cancels with this and with this. And we have minus 11 plus minus the square root of 73. That's between 8 and 9. And there is a mistake somewhere. Who tells me where? Nobody tells me where? Okay, I will get sad and tell myself, this is a plus. Plus and plus. Because this is not a 2, this is a minus 2. So the minus 1 remains. There we go. Thank you, Tarek. So the area trapped in this function, let's call this F2 and let's call this F1. I'm going to write my intersection points here. Something like this. And now the obvious problem here is that all this area will be counted as negative. So we have to do this in 3 sections. Section 1, see if I have looping. Yes, I do. Section 1, section 2, and section 3. And why do we separate them this way? So we can use the axis to our favor. Now, the surface is S1 plus S2 plus S3. Here, S1 is the integral from this point to this point of F2 minus F1. The parabola, which is above, minus a straight line, which is below. The second is the integral from 2 to 4 of it's the area that's trapped between the x-axis and the parabola. And S3 is the integral from 2 to My bad here. To this point here. Of what? If we look at it mirrored, this is the area trapped. Between this thing and this thing. So it's of F1 minus F2. Unless there is one little thing to consider here. That's what I'm going to call a reminder. What I'm going to do here, this is the integral from 2 to this thing right here. With a minus, because it's negative, we want it to become positive. Minus, with another minus, it becomes a plus. The integral, you see this small area R1? This area is the area trapped between the x-axis and the parabola. So now we have to compute all this when f2 of x is x times 4 minus x, and f1 of x is 3 minus 3/2 of x. So this type of area problems, they all have the same difficulty. You have to properly figure out what is the area that you are calculating, because otherwise trouble may emerge. So let's do it. S1 is the integral from point number 1 to 2 of this thing right here, f2 minus f1. So 4x minus x squared minus 3 and plus 3/2 of x dx. This is equal. This sums here, minus x squared plus 11/2 of x minus 3. And now we can solve this in ones because this is a polynomial. This is minus x cubed over 3. This is 11x squared. And this is minus 3x. And this is evaluated between this thing and this thing. I'm not going to calculate it. You can grab a calculator or Wolfram Alpha, Mathematica or whatever and compute this number. I'm gonna write it down somewhere. And with this, I'm going to move to the second area. Second area is a bit more user-friendly, as it's the integral of a line. Sorry, it's the integral of a parabola. S2 is the integral between 2 and 4 of 4x minus x squared dx. This is 2x squared minus x cubed thirds from 2 to 4. This is 8 minus 64 thirds, 4 in power cube, minus, we evaluate this in 2, this 32. Now we evaluate in 2, we get 8 here, and here we get 8 thirds. 32 minus 8 is 24. We have minus 68 minus 8, 56. So this is 72 minus 56. Which is 16 over 3. Looks good. The surface 1 is given by n1, surface 2 is given by n2. So now let's calculate S3. This is the integral from 2 to 11 plus the square root of 73. What? Wait. Give me a second. Anyway, so we have this integral of minus the line plus of F2 now this is 3x squared minus 3x evaluated between 2 and 11 plus square root of 73 plus 2x squared minus x cubed over 3 evaluated from 4 to 11 plus the square root of 73. What I'm going to do here is calculate the part with the numbers, and the other one I will leave indicated. So we have 3x squared, we have 5x squared minus x cubed over 3 minus 3x minus, I sum these two expressions, then I take a difference with what is below. What is below here is 3 times 4, which is 12 minus 6 And we keep doing the difference. 2 times 4 is 8. And this is 64 thirds. So this thing here is 6 is 14, which is 42. 42 minus 64 is minus 22. With this minus becomes a plus. So this thing is 5x squared minus x cubed over 3 and minus 3x evaluated in this point over here plus 22 thirds. Fair enough. And this is n3, the number that corresponds to this area. Have I done this correctly? No, I haven't. Because this thing is negative. And it shouldn't be negative. It's because this thing is negative. It is. Huh. This is a minus. This is a minus and nobody told me. Why? Because this piece is what comes with a plus. If you want to take a difference, you have to always go in that direction. However, of course, it will be minus a negative amount, so it will be a plus. Yeah, this definitely has a minus sign here. So I'm going to go back to the roots, fix the mistake. Yeah. So we have 3x squared minus 3x minus, or maybe we can flip the terms around, but whatever. 2x squared minus x cubed over 3 evaluated from 4 to 11 plus a square root of 73. So now when we evaluate these things, we have 4 terms. 2 of them depend on this thing, this ugly thing here, and the other 2 depend on numbers. So I'm going to do the same. I'm going to group them. And we have 3x squared minus x squared. So x squared. This x cubed has 2 minus, so it becomes a plus. We have x cubed over 3 plus x squared and minus 3x. This is evaluated in x equal this thing right here. And now minus this is 3 times 4, 12, minus 6, and plus 8, sorry, minus 8, and plus 4 cubed, which is 64 over 3. Now this makes a little bit more sense. The reason why is because this thing is positive now. So this is 12 minus 14 minus 2, which is minus 6/3. So this whole thing is 58 divided by 3, negative sign. And this is x cubed thirds plus x squared minus 3x evaluated in x equal this ugly thing here, minus 58 over 3. Fair enough. Now we have calculated all components of our area. Now we are ready to give a solution. It has only taken us 1,000 years, but here we are, standing tall before the problem. So the surface is n1 plus n2 plus n3, which is equal to, well, first of all, n1, which we evaluate, we have minus 8/3 plus 44 minus 6 minus plus 16/3, which is this part here, and plus n3, which is that part there. So I'm going to call this, I don't know, M1, and I'm going to call this M2, and I'm going to put the numbers a little bit together. This is M1. Plus M2, and now in order to gather all this thing a little bit, we found that minus 8 minus 58 is minus 64. And plus 16 is none other than 48. So all this thing sums minus 48/3. And this is 38. Now, the magic with this is that 48 is divisible by 3. It's exactly 16. So our total area is minus M1 plus M2 minus 16 plus 38. Now, it's time for questions. If nobody asks me everything, I won't believe it. So please go on. Okay. All right, so let's move on. We have two curves. When will the exam results come out? They really should come out at any moment now. I finished correcting them yesterday and I sent them to Jonah, so you will see your results soon, I hope. So that's the sine of x. And sine square of x is something on this line. Now, who tells me why this is true? This exercise can't go on until we verify whether this is true or not. So please tell me. I mean, the day of tomorrow, you might get to, I don't know, exam 2 and be asked this exercise. And if you don't know whether sine of x or sine squared of x is the greater function, you're not going to be able to solve this. So, fundamentals. When you insert the x values, you can see that the y value will be less for sine squared of x. That's not a proof. Unless you can try every single value in this interval. Spoiler alert, that will take more time than the age of the universe. So, I'll go on. Any questions about this?
Just a question. What is that bar behind sine x before the last? No, after. No. Same line, but after. Next one. Next.
This is a
Yeah.
1.
Okay, cool. Thank you.
So, for those of you in the background who may or may not have questions but won't ask them, these kind of things is the 101 of analysis. When the grades of your exams arrive, you will probably not be happy. And the reason why is because you haven't gotten your hands dirty enough, like not even close. So pick up any topic that you are really not completely feeling and destroy every single one of the exercises until these things come natural to you, because that's the way. I can show you how to do integrals, I can show you areas, I can show you whatever. If you don't pick up the book, sit down and solve everything you can, all my work and all your work being here is worth nothing. So let's do it. I'm doing my part. I just need you to do yours. For you, especially. So we have two functions, and we know that one of them is strictly larger than the other. So that area S is the integral in the working interval we're using of the greater minus the smaller. The first integral, we know it already. And the second one, we will use the only trigonometric identities that I know. We calculate the difference between these two expressions, and we have 2 sine squared x and with this we can go on. Minus, with this minus becomes a plus. So this is cosine of 0 minus cosine of pi halves. This is 1 and this is 0. So this is 1. Minus integral of a constant, the constant times the length of the interval. Pi fourths. Pi halves times 1/2. For this last one, we have 1/2 times 1/2 sine 2x, evaluated between 0 and pi halves. Now this is 1/4. So this is 1 minus pi fourths plus 1/4 times the sine of pi, 0, the sine of 0, 0. So the area trapped between those two is 1 minus pi fourths. Now, I want to hear you guys and girls in the background. Questions about this? All right.